Today I made the video on steriochemistry of organic compounds. Introduction. One of the most important characteristics of organic compounds is their ability to show isomerism. Isomers are compounds which have the same molecular formula but different chemical and physical properties. It is of the two types, structural isomerism and stereoisomerism. Structural isomerism, compounds having the same molecular formula but have different structures, different arrangement of atoms within the molecule are called structural isomers, and the phenomena is called structural isomerism. It is of the following six types: chain or nuclear isomerism, compounds having the same molecular formula but different arrangement of carbon chain within the molecule are called chain or nuclear isomers, and the phenomena is called the chain or nuclear isomerism. For example, the formula C4H10 represents two chain isomerism. Butane and normal butane and 2-methyl propane is isobutane. Similarly, the formula C5H12 represents three chain isomers: pentane, normal pentane, 2-methyl butane, isopentane, and the 2,2-dimethyl propane, which is neopentane. Likewise, the molecular formula C6H14 represents 5 chain isomers: hexane, which is N-hexane, 2-methyl pentane, which is isohexane, and 3-methyl pentane. Fourth one is 2,2-dimethyl butane, and the next one is 2,3-dimethyl butane. Second is position isomerism, compounds which have the same molecular structure of the carbon chain but differ into the position of the multiple, double or triple bond of the functional group are called position isomers, and the phenomena is called position isomerism. For example, but1-ene and but2-ene are position isomers. First one is but1-ene, second but2-ene, likewise 1-but-ine and but2-ine, and beta-1,3-diene and beta-1,2-diene show position isomerism. Similarly, propane-1-ol and propane-2-ol are position isomers. Third one is functional isomerism. Compounds having the same molecular formula but different functional group are called functional isomers, and the phenomenon is called functional isomerism. For example, the molecular formula C2H6O represents the following two functional isomerism: ethanol and methoxymethane. Similarly, the molecular formula C3H6 represents the following four functional isomers: propane-one, which is acetone, and the propanol, which is propanoaldehyde. Next one is prop2-ene-1-ol, which is allyl alcohol. Next one is ethoxyethane, which is methyl vinyl ether. Further example of functional isomers are first one is carboxylic acid and ethers. C2H4O2 represent the ethanoic acid and methyl methanoate. Aldehyde and ketone C3H6O represent the propanone and propanol. Third one, C part is diene and alkynes. C4H6 represent the beta-1,3-diene and but1-ine or but2-ine. D1 is alkenes and alkynes. C4H6 represent the but1,2-diene and alkene and but1-ine or but2-ine. Nitroalkenes and alkyl nitrines C2H5NO2 represent the nitroethane and the ethyl nitrite. F part is primary, secondary, and tertiary amines. C3H9 and represent the propane-1 amine, primary amine, and methyl ethane amine, secondary amine, and N-dimethyl methane amine is tertiary amine. G part is cyanides and isocyanides. C2H3 and represent the CH3 C1, which is ethane, nitrile, and methyl isocyanide. H1 is aromatic alcohols, phenols, and ethers. C7H8 represent the benzyl alcohol, anisole, O-cerol, M-cerol, P-cerol. It may, however, be noted that the O-cerol, metacerol, and paracerol are themselves position isomerism. Fourth one is metamerism. Compounds having the same molecular formula but different number of carbon atoms or alkyl groups on either side of the functional group, oxygen, sulfur, NH, and CO are called metamerism, and the phenomena is called metamerism. Metamerism occurs among the members of the same homologous family. For example, ethoxyethane is a metamer of 1-methoxypropane or 2-methoxypropane. B part is diethyl ether is a metamer of methyl and propane thioether and or isopropyl methyl thioether. C part is diethylamine is a metamer of methyl and propylamine and isopropyl methylamine. D part is pentrione is a metamer of pentane 2-one or 2-methylbutane 2-one. It may be noted that the members may also be position isomers. For example, pentane 2-one and pentane 3-one may be regarded as position isomers as well as metamers. First one is deuteromerism. It arises due to the 1,3 migration of hydrogen atom from one polyvalent atom to the other within the same molecules. Isomers thus obtained which exist in dynamic equilibrium with each other are called deuteromerism or phenomena is called deuteromerism. There are several types of deuteromerism, but ketoenol deuteromerism is the most important. It is the type of deuteromerism or from deuteromerism contains the keto groups while the other contains the enolic group. Two simplest examples of ketoenol deuteromerism are acetaldehyde and acetone. In simple aldehyde and ketones, the amount of enolic form is negligible small. However, if the enolic form is stabilized by intermolecular hydrogen bonding chelation, as in 1,3-dicarbonyl compounds, the amount of enolic form is much greater than the acetaldehyde or acetone. For example, in acetone, acid ester, the amount of enolic form is 7%. Similarly, acetone is 1,3-diketone also exhibit ketoenol deuteromerism, but the amount of enolic form here is much higher, 70%, than even in acetonic acid. This is due to the reason that keto group is a better, much electron withdrawing group than the ester group. Essential condition for an aldehyde or ketone to exhibit ketoenol deuteromerism, it is essential that it must have at least one alpha hydrogen atom. That thus acetophenone but 2,1 and propanaldehyde all contains alpha hydrogen atom and hence so ketoenol deuteromerism. First one is acetophenone, second one is butene, and third one is propanaldehyde. They have the alpha hydrogen. In contrast, benzyl aldehyde, benzophenone extra do not show ketoenol deuteromerism because do not have contain alpha hydrogen. Similarly, nitro compound also show deuteromerism. Nitromethane, after reaction it form acid form. Sixth one is ring chain isomerism. Compounds having the same molecular formula but possessing open chain and cyclic structure are called ring chain isomers, and the phenomenon is called ring chain isomerism. For example, first one is C3H represent propene and cyclopropene which are ring chain isomers. B part is C4H8 represent butane and cyclobutane or methyl cyclopropane which show or ring chain isomers. Similarly, butane CH3 CH3 or 2-methylpropane are chain isomers of cyclobutane and methyl cyclopropane, propane and cyclopropane which show ring chain isomers. Double bond equivalence is called index number or the index of hydrogen deficiency. The problem and the structure isomers determination of organic molecules can be easily solved by the concept of double bond equivalence, which implies the sum of double bond and ring present in the molecule. It is the relation between the double bond equivalent is sigma n v minus 2 divided by 2 plus 1, where n is the number of different kinds of atoms present in the molecule and v is the valency of the each atom. For example, double bond equivalents for MfC3H6O is 1. This means the various structure isomers of C3H6 which may contain either one double bond or one ring homocyclic or heterocyclic is as discussed below in example 3.2. Likewise, two double bond implies either two double bonds on one triple bond and or two rings or bond plus one ring. Similarly, for double ring variant implies either four double bonds or two triple bonds or the two double bond plus one triple bond or one or three double bond plus one ring, benzene ring or any other combination of ring double and triple bonds. Example 3.1 or divide all the possible cyclic structure isomers of hydrocarbons with the molecular formula 68, and the answer is 2. First isomers First isomer contain a triple bond R pent1 second one is 3-methyl-butene and third one is pent2ine. Acyclic isomers containing two double bonds are penta 1,3-diene. Fifth part is 2-methyl-butene 1,3-diene penta 1,4-diene. Then is penta 1,2-diene and 3-methyl-butene 1,2-diene, and the next one is penta 2,3-diene. Thus there are in all 9 acyclic structure isomers having molecular form mass 60 and molecular formula is C5H8. Cyclic isomers containing one double bond and one ring cyclopentane and one methyl cyclobutane, 3-methyl cyclobutane and methyl ethanol cyclobutane, and next is 1,2-dimethyl propane cyclamine 1, and the next is 1,3-dimethyl cyclopropane 1 in 7th part is 1-ethyl cyclopropane, 8th part is 3-ethyl cyclopropane 1 in 9th part is 1-ethanyl cyclopropane, and 10th part is ethyl diene cyclopropane, and part is 1,1-dimethyl cyclopropane. B part is isomers containing two rings. First example is bicyclo 2,1,0 pentane, and next one example is 1-methyl bicyclo 1,1,0 butane, and next one is 2-methyl bicyclo 1,1,0 butane. Thus there are in all 14 cyclic structure isomers with molecular formula 60 or molecular formula C5H8. All acyclic isomers have the molecular formula C3H6O. Double bond equivalence is 1, and therefore C3H6O may contain C double bond C and or C double bond or adding the following 7 isomers are possible. Acyl isomers: first is acetone, second is propanol, third is propane 2 in 1 all, and next one is methoxyethane. Cyclic isomers are oxetone, next one is 2-methyloxyrane, and the next one is cyclopropanol. Thus C3H6 are 7 isomers. Note violating the structure isomers for any given molecular formula. Tautomers are neglected unless otherwise asked for. Example: tautomers of acetone C2 CHOH CH3 and have two of propanol CH3 CHCHOH have not been included while containing the total number of structure isomers. Next is stereoisomerisms. Isomers which have the same molecular same structure formula but have different relative arrangement of atoms or groups in space are called stereoisomers. Greek stereo means space and meros means part, and the phenomena is called stereoisomerism. Stereoisomers are of following two types: conformational isomerism, stereoisomers which differ in the relative position of atom in the molecules which have the interconverted simply by the rotation above the sigma bond are called conformational isomers. In the other word, the inversion of these isomers does not require breaking or remarking of covalent bond. Second one is configuration isomers. Stereo isomers which can be interconverted only by the breaking the remarking of covalent bond and not simply by rotation about sigma bonds are called conformational isomers. There are the following two types: optical isomers and geometric isomerism. Optical isomerism or certain compounds can exist in the two stereoisomeric form which cannot be superimposed on another in spite of this difference in the relative spatial arrangement of atoms. These atoms have identical physical properties such as melting point, boiling point, effective index, density, solubility. They also resemble one another in most of their chemical reactions. However, they differ only in their behavior towards plane polarized light. One rotates the plane of polarized toward right but other towards left, but to some extent such a pair of compounds are called optical isomers and the phenomena is called optical activity. Some general concept about the optical isomers. In order to understand the phenomena of optical isomerism, we must be familiar with the following terms: plane polarized light. Ordinary light consists of electromagnetic waves of different wavelength. Monochromatic light, on the other hand, consists of waves of only one wavelength. It can be obtained either by the passing the ordinary white light through a prism or grating, or by the using a source which give light by of only one wavelength. For example, sodium lamp emits yellow light of about 589.3 nanometer wavelength, where it is ordinary light or monochromatic light and consists of a having vibration in all the planes perpendicular to the line of propagation of light. In such a beam of light is passed through a nickel prism made from a particle crystalline from Maceous 3 known as calcite. The light that comes out of the prism has vibration only in one plane. Such a beam of light which has vibration only in one plane is called plane polarized light. The nickel prism used to obtain plane polarized light is called the polarization, and is the angle of rotation. The angle is in the degree through which the plane of polarized light gets rotated and passing through the solution of an optically active compound is called the angle of rotation. It is denoted by the Greek letter alpha. Polarimeter, the instrument used for measuring the angle of rotation of the plane polarized light, is called polarimeter. It consists of a light source, usually a solid lamp, sodium lamp, two nickel prism or polarimeter tube. The nickel prism near the light source is called the polarizer, while the near the eye of the observer is called analyzer. The axis of polarization of polarizer is fixed, while that of analyzer can be changed in the between. The polarizer and the analyzer is produced a glass tube, and the polarimeter tube contains the solution of the optically active substances. The solid represent the plane polarized light before the broken line represent the after passing through the sodium of the optically substance. If the axis of the polarization of the two nickel prism in held parallel in shown figure in 3.2 to each other, and the polarimeter tube is embedded, the plane polarized light from the polarizer passes through the analyzer without any change in intensity. Conversely, if the two nickel prisms are held with their axis of polarization perpendicular in each other, no light passes to all. However, when the solution of any optically active compound is placed in between the polarization and the analyzer with their axis of polarization parallel to each other, the intensity of light coming out of the analyzer is much less than the feeling on the polarization. In some cases, in order to have the maximum transmission of the light, the analyzer has to be rotated through some angle in one direction to the other. This angle through with the analyzer has to be rotated to get the maximum transmission of the light is called the angle of rotation. The angle of rotation alpha of the optically active compound depends upon the following factors. First is the nature of the optically active substance. Second is the concentration of the solution in gram per milliliter. Third one is the length of the solution through which the light passes. Fourth is nature of the solvent. Fifth is the wavelength of the chromatic light used. Sixth one is temperature of the sample. Fourth part is specific rotation. In order to compare the radiative powers of different optical active substances, the optically activity is usually expressed in terms of specific rotation. The specific rotation of an optically active substance is defined as the degree of rotation observed when the wave polarity is passed through a tube having a path length of 1 decimeter, 10 centimeter, and a concentration of 1 gram per milliliter of the compound at a specific temperature and wavelength is denoted by alpha T, where T is the temperature and is a wavelength specified temperature and of light used. Usually, D line of sodium vapor lamps having a wavelength of 589.3 nanometer is used as the source of the monochromatic light. Since it is not always possible to dissolve 1 gram of the optically active substance in 1 milliliter of the solvent, therefore the measurement of the angle of rotation is usually carried out of the some lower concentration. The specific rotation is then calculated by the application of the following equation. Alpha T is equal to observed angle of the rotation alpha by LC, where L is the length of the polarimeter tube in decimeter and C is the concentration of the substance in gram per ml. While reporting the specific rotation of optically active substance, it is customary to include the concentration of the solution used for measurement along with the solvent used for making the solution in the parent has after the specific rotation. For example, the specific rotation of the cane sugar is 293 Kelvin. The sodium vapor is D293. D is equal to plus 66.5 degrees. C is 0.202 gram per ml water. The sign before the angle of rotation denotes the cane sugar is dextrorated, just like melting point, boiling point, and the refractive index, etc. The Successive rotation is a characteristic property of optical active compounds. Optically activity discovery. The phenomena of optically activity was discovered by the French chemist Louis Pasteur in 1848 to observe that when a concentrated sodium or sodium ammonium titrate was allowed to crystalline, the type of crystal represented out, working carefully with a magnifying glass and a pair of tweezers to Pasteur to able to separate the crystals when the two piles, one of the right-handed and the other is the left-handed crystals. Each type of crystals when dissolved in water was found to rotate the plane polarized right. One solution rotates the plane of polarized right towards while the other towards the left, but the same extent later on millions of molecules have been discovered which rotate the plane of polarized right. Some substances which can rotate the plane of polarized light are called optically active isomers. Optic isomers substances and the property of a substance to rotate the plane of is called optically activity, which rotate the plane of towards right in the clockwise direction is called dextrorotatory. Dextro means right and usually present by the prefix d and the positive signs. On the other hand, the substance which rotates the plane of towards left in the anti-clockwise direction is called levorotatory. Latin levos means left and is usually present by the prefix l or minus sign. Clarity and inspection of the molecular structures of optically active compounds indicate all the compounds have chiral or disymmetric molecules. Molecules of an object is said to be chiral or disymmetric if not superimposable on its mirror image, and the property of non-superimposability is the chirality. On the other hand, a molecule of an object which is superimposable on its mirror image is called achiral and non-disymmetric or symmetric. To understand the term chiral and chiral, let us consider the alphabet P and A, whereas P is a chiral and A chiralation is figure 3.3. Similarly, the alphabet F and G are chiral, while M and O are achiral. The most common example of chiral object is the human hand. If you hold your right hand before a image, the image looks directly at the right hand. If you do not have a mirror available, hold your hand together within the palms facing each other. You can see that there are mirror images. Try to superimpose your hands, both palms down. You can not do it in figure 3.4. The human hand is chiral. Similarly, gloves shows a chiral objects. Have you ever thought why cannot you wear the left-handed gloves in the right hand? This is because there are no superimposable mirror images of each other. A button of sphere, a cube, and the most shocks on each hand are achiral since they are superimposable and their respective images figure in 3.5. Molecular chirality and the aromatic carbons. Let us now extend the concept of chirality to organic molecules. The chirality in organic molecules arises due to the tetrahedral or sp3 hybridized nature of the carbons. The four valences of carbon are directed towards the four corners of a regular tetrahedron as proposed by the J. Want, Half and C. Bell independently. To illustrate this process, understand. To illustrate this, let us consider a molecule of 2-chlorobutane A. In the molecule, C2 carbon is attached to the four different substituents HCl, CH3 and CH3CH2. Such a group atoms which is attached to the four different substituents atom or group is called the aromatic carbon atom or a chiral carbon atom, or simply a chiral center. A chiral carbon atom is indicating by a asterisk. Further, it may be noted that it is this carbon which makes the molecule disymmetric or chiral is explained below. The mirror image of A is A1. To check the superimposability of A1 over A, rotate the molecules through 180 degrees in such a way that the Cl bond in the new structure A2 projects the same direction as in the structure A. Now superimpose A2 over A. We find that the A and A2 are superimposable figure in 3.6a. No matter how we turn the twist the molecule without breaking the bonds, we may get the central carbon atom and the two are of the atom superimposed. For example, C and HCl can be superimposed, but the spatial orientation of CH3 and CH3CH2 groups are different in A and A2. In structure A, CH3CH2 is pointing towards U, while in Ca2 it is pointing away from U. Thus, A and A2 are superimposable mirror images, and hence 2-chlorobutane is a chiral molecule. However, if the two substituent atom or group attached to the carbon atom are similar, the chirality of the dismetric is lost and the molecule becomes symmetric or achiral. Since a simple position rotation through 180 degree about its rotation will make it superimposable on its mirror image. For example, consider the molecule of 2-chloropropane B and its mirror image is B1 in figure 6.3b. To check the superimposability of B1 over B, rotates the molecules from 180 degree to get the B2. Now let's try to superimpose structure B2 over B. You can find B and B2 are superimposable, hence 2-chloropropane is an chiral molecule. From the above discussion, it follows the chirality probably arises due to the presence of asymmetry of the chiral carbon atoms, as we shall discuss later in this unit. This statement, however, it is not always true. Nevertheless, the presence of one chiral or asymmetric carbon atom in a molecule always make it chiral. Hence, the optically active, for example, lactic acid, glyceraldehyde, or 2-dihydroxypropenyl bromochloroidomethane are the chiral or dismetric molecules, hence are optically active. Thus, the necessary and sufficient condition for a compound's be optically is not just the presence of one or more asymmetric or chiral carbon atom, but its chirality or dismetric or molecule as a whole. Elements of asymmetry. The superimposability of an object or a molecule and its mirror image can be tested within the help of three elements of symmetry. Such a plane of symmetry is or a center of the symmetry, and the alternating axes of symmetry. Chiral object or molecule do not have an element of symmetry. On the other hand, a chiral object or molecules have at least one or two more elements of symmetry. First is plane of symmetry or mirror image or sigma plane. The most commonly observed elements of symmetry in a plane of symmetry or mirror plane or a plane sigma plane is defined as an imaginary plane which divides the molecule into two equal halves, such that the one half of the molecule is mirror image of the other. It may pass through atoms between the atom or both. Thus, a sphere in figure 7.3a is a chiral since it is the plane of symmetry, and on the other hand, human hand left or right or left is a chiral since it has no element of symmetry. In figure 3.7b, a vertical plane has been shown, but it is not a plane of symmetry since it is divided the hand into the two equal halves. Like objects, some molecules also possess a plane of symmetry. For example, to chloropropane figure 3.8a has a plane of symmetry which is perpendicular to the plane of paper and passes through Cl, C and H atoms. Similarly, mesotitric acid has a plane of symmetry which is perpendicular to the plane of paper and passes through midpoint of C bond. Therefore, both these molecules are chiral since they can be superimposed on their respective mirror image, hence are optically inactive. On the other hand, molecules of 2-butanol and the lactic acid is figure 3.8 do not have a plane of symmetry, hence are chiral. As a result, they cannot be superimposed on the respective mirror image, hence are optically active. And figure 3.8 and figure 3.9. In figure 3.8, the plane of symmetry is the 2-chloropropane and the mesotitric acid, and in figure 3.9, the 2-butanol and the acetic acid are chiral molecules due to the absence of the plane of symmetry. In center of symmetry is defined as the point from which lies hand drawn on produce an equal distance on the other side. We meet identical points, atoms or groups. It is also a center of inversion and is usually denoted by the symbol Ci. For example, both trans 1,3-dimethylcyclobutane figure 3.10 a mesotartic acid figure 3.10 we have a center of symmetry, hence are called optically inactive. Third is alternating axis of symmetry. A molecule is said to be a possess an unfold alternating axis of symmetry rotation through an angle of 360 by and about this axis, and then followed by the reflection in perpendicular to the axis given a molecule which is indistinguishable from the original molecule. Consider, for example, the molecule A shown in the figure 3.11. Hence, Z positive and Z negative present the chiral groups such CH3C2H5 and the CH3C2H5 presently, respectively. Rotation of molecule A through 90 degree about axis AB and passes through the center of the ring and the perpendicular to its plane give molecule B. The reflection of B gives the original molecule A. Thus, this the molecule have a fourfold 360 upon 90 is equal to 4 alternating axes of symmetry, hence is called a chiral. Since one fold alternating axis corresponds to a plane of symmetry and the two fold alternating axes correspond to the center of symmetry, therefore absence of alternating axis of symmetry is unnecessary and the sufficient condition for a molecule to exhibit optical activity. Next one is the relationship between the asymmetric dissymmetry and the chirality. It is interesting to note that while describing optical activity of the organic compounds, the two terms asymmetric and dissymmetric have been used without any distinction. Yet there exists a suitable difference between them and the molecules which have no elements of symmetry. Alternating or simple axis of symmetry is called a symmetric molecule. Such a molecule is usually optically active. On the other hand, a molecule which have no alternating axis of symmetry but may or may not have a simple axis of symmetry is called a symmetric molecule. Like symmetric dissymmetric molecules are usually optically active. Consider the example of 2-butanol is no element of symmetry. It is an asymmetric molecule, hence is optically active. Now consider the projection formula of the optically active tartaric acid. First, it has a simple axis of symmetry in the center of the molecules. It shown by a dot and passes perpendicular to the plane of paper rotation through 180 degree. About the axis give formula 2 and which include with the original formula. First, the optically active tartaric acid has a simple or C2 axis of symmetry, hence it is not an asymmetric molecule but is a disymmetric molecule. Nevertheless, it is optically active. Thus, all the asymmetric molecule and the disymmetric, but all disymmetric molecules are not asymmetric. Although both of them are optically active. To avoid this confusion, another term called chirality has been introduced and is more widely used there. In simple rotation, optically active with the no superimposable mirror image relationship and no to the absence of the element of symmetry. The same molecule is said to be chiral and hence optically active if its mirror image is not superimposable. Let us now draw mirror image. Third, structure 1. Since structure 3 is the superimposable of structure 1, therefore, the tartaric acid is a chiral and optically active even though it contains C2 axis of symmetry. Thus, and we conclude that the higher planes of symmetry and the symmetry preclude chirality compounds which have the only simple axis of symmetry and can be chiral and hence optically active. Stereogenic center or the stereo center, we have started about the tetrahedral carbon atoms attached to the 4 different atoms or the are called asymmetric or the chiral carbon atom. However, in the 1984, J. Milsom and J. Siegel pointed out that the use of the term chiral carbon atoms has created conceptual confusion. According to the scientists, it is not the atom which is chiral but different. It is the molecule which is chiral. In the other word, chirality is the geometric property which prevails, tends and affects all the part of the chiral molecule. For example, all the atoms of 2-butanol are in all chiral environment, hence all are said to be chirotropic. However, we have not used the term chiral carbon atom such as C2 and 2-butanol in the same sense. We have simply used this term to indicate that if any two atoms attached to this ring carbon are mutually exchanged in new stereomers is obtained. Figure 3.12a. In other words, C2 of 2-butanol should be distinguished as a center of stereoisomers or stereogenic center and not as a chiral center. Further, consider the cis and trans stereoisomers of 1,3-dichlorocyclobutane. Figure 3.12 3.12b. Here carbon atom 1 and 3 are the center of a stereoisomerism but not the chiral centers, since each carries two identical groups. Therefore, these are preferably called a center of symmetric and stereogenic center. The stereogenic center may or may not be chiral center of chirality. For example, the stereogenic center C2 in the 2-butanol is chiral C1 and C3 and cis or trans 1,3-dicyclobutane is a chiral. Thus, all the chiral centers are stereogenic, but all stereogenic centers are not the chiral centers. Therefore, in this unit, henceafter we shall use the term stereocenter and the stereogenic center instead of the chiral centers. Next one is configuration and the Fischer projection. Stereoisomers have the same molecular formula but different relative arrangement of the group or atoms in space. The spatial arrangement of a group or atom which character so defines a particular stereomer. It is called this configuration. This configuration of organic molecules can be best visualized by the impression of the model or three-dimensional 3D structure. Depending upon how you hold the molecule, the 3D structure of an organic compound may be represented in the number of ways, but the most commonly used 3D model in the flying waves model. In this model, three types of lines are used. A solid line waves, a thick solid line represents a bond line above the plane and the paper including towards the observer. Ordinary solid lines represent bond lines within the plane of symmetry, while the dotted waves represent a bond line below the plane of the symmetry and projecting away from the observer. In this method, sometimes the dotted wave is replaced by a dotted line for the purpose of simplicity. Figure 3.13 is flying waves model of a stereomers of CHXYZ. However, it is not always convenient to construct this model or draw their three-dimensional structure. It therefore becomes necessary to devise some method to represent three-dimensional structure or two-dimensional structure, such as a paper, a blackboard. In 1891, the German chemist Emil Fischer introduced a simple method to represent the spatial arrangement of atoms or groups around chiral center on a paper. These planar representation are called Fischer projection. The main point of procedure as given in below. For the molecule of an chiral compounds containing the chiral center is viewed in such a way that the group or bonds attached to the chiral center are horizontal and point towards the observer, while the other two are vertical and point away from the observer. Figure 3.14. Figure 30.14 is Fischer projection for minus lactic acid. What is the various atoms or group attached to the chiral center and projected on the plane of paper in the form of cross. By convention, the chiral center is shown, but it is not viewed at the intersection of horizontal and vertical bonds. Third part is if the chiral molecules contains two or more chiral center, each chiral center must be viewed individually in the manner described above. Fourth part is as far as possible the vertical part of the position formula thus obtained should represent the largest chain of the carbon atom within the most oxidized carbon COH in lactic acid and CHO in the glyceraldehyde CH2OH into methyl 1 metanol. At the top, this carbon atom is then numbered according to IUPAC nomenclature. To a three-dimensional structure a molecule from the Fischer position, we simply devise the process described above. In figure 3.15, for example, conversion of Fischer position formula of D positive glyceraldehyde into three-dimensional structures. In figure 3.15, depending upon the bonds are drawn in the horizontal, which bonds are drawn in vertical position, several Fischer position can be written as for the same compounds. It is therefore necessary to compare two different positions to see whether they represent the same or different compounds. To test the identity of a different Fischer position for the same compound, for the following rule must be observed. First one is a Fischer position must not be plane of symmetry and the turned over. Such an operation gives the enantiomer of the original molecule. For example, structure 1 and 2 represent the enantiomer of bromochloromethane. Second is a Fischer position may be written in through 180 degree in the plane of such an operation gives the same stereoisomer. For example, structure 3 and 4 represent the same stereoisomer of lactic acid. Third part is a Fischer position should not be turned over through 90 degree and 270 degree in the plane of symmetry of a paper. Such an operation gives the enantiomer of the original molecule. For example, 5th and 6th represent the enantiomer of 2-methylbutanol. Fourth part is one may interchange the group attached to the chiral carbon and each 2 or 4 number of time a future position without affecting the configuration of the molecule. In a unity, the number of interchanging should be even no matter which groups are exchanged. A useful quality of the rule is that we can hold any one group steady and rotate the other three in either clockwise or anti-clockwise direction. For example, in the COH group in the future projection, seventh part N for aniline is fixed and the other three groups attached to the clockwise direction of projection 8 and 9 are thus obtained are identical and represent the same isomers of aniline. And is optically isomerism. All the optically active compounds exist in the two or more stereoisomer form. They differ from another relative spatial arrangement of the group of atoms. The stereoisomers which resemble one another in their chemical reaction and the most of the physical properties but differ only in the behavior towards when peroxide are called the optical isomers and the phenomenon is called optical isomerism. Optical isomerism in the compounds containing one chiral, one of the stereogenic center and the enantiomer. This is the simplest kind of optical isomer and was discovered by the French chemist Louis Pasteur in 1848 as stated above. The optically active compounds can exist in two or more isomeric form are called optical isomers. Optical isomers which are non-superimposable minimums of each other and the enantiomer and the phenomena is called enantiomers. The enantiomer have identical physical and chemical properties but rotate the plane of opposite in opposite direction but the same extent. To understand the phenomena of the enantiomer, let us again consider the molecule of bromochlorofluoromethane. It exists in the two isomers forms 1 and 2 which are the non-superimposable images of each other. Figure 1.16. Further, each of the two isomers is optically active and rotates the plane of peroxide in the opposite direction but to the same extent. This first and second represent enantiomer of the bromochlorofluoromethane. The enantiomer which rotates the plane of peroxide towards the right is called the dextrorotatory and is represented as D is positive, while the enantiomer which rotates the plane of peroxide towards the left is called the levorotatory and is represented as L negative. However, it is maybe emphasized that there is not possible as tell to which isomer is positive and negative just by looking at the structure is to determine experimentally. Figure 3.16 is enantiomer of bromochlorofluoromethane. Similarly, acid and the butane to all both show enantiomer. Figure 3.17 since their molecules cannot be superimposed on their mirror image. Enantiomer of part A is lactic acid and the second part is butane to all. Condition for enantiomers. It may notice the necessary and sufficient condition for a molecule to exhibit enantiomers and hence optical activity is chiral symmetry of molecule and a mirror image of must be superimposable. It may or may not be contain chiral asymmetric momentums. Usually the presence of one or two chiral carbon atom causes a molecule to show an enantiomer, hence optically active by certainly it is not the necessary and sufficient condition. For example, tartric acid and the contains two chiral carbon atom marked as asterisks but does not show enantiomer and actually optically active. Tartric acid has optical activity, contains promiscuity and does not show enantiomerism. This is the reason that it contains a plane of symmetry which divides the molecule into two equal halves so that one half of the molecule is the mirror image of the other. If, as a result, mesotartric acid and this mirror image and superimposable in the other words, mesotartric acid is a chiral and a non-symmetric or symmetric molecule, hence it is not show an enantiomer or optically activity. Thus, the optical activity of mesotartric acid is due to the internal compensation. The rotation caused by the one half of the molecule is actively concerned by the one unequal or opposite rotation caused by the other half of the molecule. On the other hand, there are many compounds which do not contain chiral carbon atom but their molecules are chiral and symmetric, hence they enantiomer are optically active. For example, alkenes figure 3.18 A and orthodistributed diphenyls in figure 3.18 B do not contain chiral carbon atom but their molecules non superimposable on their respective mirror images, hence show enantiomer optical activity. Figure 3.18 A part is enantiomer of penta-2,3-diene and alene and B part is enantiomer of C6-dinitrodiphenylic acid. Properties is of enantiomers. The important property of enantiomers are given below. First one is they have identical physical properties, so as melting point, boiling point, density, solubility, refractive index, etc. Differ only in the direction of rotation of the plane polarized light. One rotates the plane of polarized light towards the right and the other towards left to the some extent. Enantiomers have identical chemical bodies extend towards optically active rays, and the chemical reaction of the enantiomer of any optically active compound with optically inactive reagents chiral such as HBr, H2SO4, CS3, COH, etc. are only the same but occurs at the same rate. For example, the two enantiomer of 2-butane to not only give the same alkyne to butane and the treatment of the concentrated H2SO4, but the rate of these reactions are also identical. On the other hand, the reaction of enantiomer with optically active reagents, chiral reagents produced in the same rates. For example, if we separately esterified the enantiomer of 2-butanol with negative lactic acid, the rate is found to be different. The third one is enantiomer have different biological properties. In biological system, all reactions are catalyzed by enzymes which themselves are optically active compounds. The reaction of enantiomers, which enzymes are stereospecific, that quite often then the reaction of one of the enantiomer does not take part at all. For example, we eat a lot of dextro glucose in the form of carbohydrate. It is metabolized in the body to produce CO2 and H2, and a lot of energy is generated. This energy we use for our day-to-day work on. However, if we eat liver glucose, it is metabolized and it is extracted by such as through the urine. Similarly, the negative quinine brings down the malaria fever and the positive quinine. This difference in reactivity of enantiomer is the great importance of biochemistry and the chemistry taking place in our body. Chiral molecule with the two stereogenic centers or optical enantiomer in compounds containing two stereogenic centers. So far we have discussed that the presence of one stereogenic center or the chiral asymmetric carbon also make the molecule dissymmetric or chiral. As a result, compounds containing the stereogenic centers or chiral carbon atoms can exist in the two stereomers known as enantiomer. Therefore, it is accepted that the compounds which contain two or more stereogenic centers will exist in more than two stereogenic forms. To examine this, let us now discuss the optical isomers of compounds containing the stereogenic centers. These two stereogenic centers can be either dissimilar when the atoms or groups attached to the one chiral carbon are different from those present on the other, or similar when the atoms or groups attached to the same. Two representative examples of such compounds are 2,3-dichloropentane and tartaric acid. The 2,3-dichloropentane is dissimilar stereogenic center and the tartaric acid is similar stereogenic center. Let us now discuss the optical isomers in each one of them separately. Compounds with the dissimilar stereogenic diastereomers. Compounds such as 2,3-dichloropentane contain two dissimilar stereogenic centers, hence can exist in four stereomers. Isomeric forms, first, second, third, and fourth are optically active. Stereomers 1 and 2 are non-superimposed mirrors of each other, hence represent a pair of enantiomer. One of these enantiomer is dextrorotatory while the other is levorotatory. Likewise, the stereomers third and fourth are non-superimposable mirror images of each other, hence represent another pair of enantiomers are retrorotatory and the other is levorotatory. Thus, compounds contain the two similar stereogenic centers exist in four optically enantiomers, which can be regarded as a pair of enantiomers. Now, the question arises to what is the relation between any two other pairs such as first and third and first and fourth and second and third or second or fourth, and inspection of their structure reveals that none of the species are images of each other and are called diastereomers and simply diastereomers. Thus, first, second, third represent a pair of diastereomers. In other words, diastereomers are stereomers which are not enantiomers. They have the same configuration at the stereocenter of the chiral carbon but different at the position. Convince yourself by examining the structure. Properties of diastereomers. Since diastereomers are the stereomers which are not mirror images of each other, the properties of the different from those of enantiomers, which are mirror images of each other. Some important properties of diastereomers are physical properties, melting point, boiling point, etc. Unlike enantiomers, diastereomers have different physical properties such as melting point, boiling point, is in a given solvent density, refractive index, etc. And its preparation due to the difference of physical body diastereomers, unlike enantiomer, can be separated by the physical method of separation as such. Fraction distillation is chromatographic behavior towards the primary diastereomers may be either optically active or inactive. For example, geostereometric isomers, which are regarded as the diastereomers, are optically active, while others are usually optically active. Even the enantiomers, active diastereomers may have the same or opposite signs of rotation. Third part is chemical properties. Unlike enantiomers, diastereomers have similar but not identical chemical properties. Thus, the rate of reaction of diastereomers with chiral reagents are generally different. This is due to the reason that the neither the reagent nor the transition state are mirror images of each other. As a result, diastereomers have different energy of activation of particular reaction and react to the different rates. Optical isomers in compounds containing two dissimilar stereogenic center and the mesocompound. The most important example of compounds containing two similar stereogenic centers shown by the asterisk is tartaric acid. Like 3 dichloropentane is tartaric acid and its principle can exist in four stereoisomeric forms: first, second, third, and fourth. There are no superimposable mirror image. Enantiomer and third and fourth is superimposable images represent only one stereomers. Stereomers one side are mirror images of each other and neither superimposable or inconvertible or by rotation after carbon-carbon bond. Thus, they are enantiomer of the this enantiomer is dextrorotatory and the upper positive tartaric acid and the other is lower rotatory negative tartaric acid. Stereomers third and fourth are the mirror image of each other but becomes superimposable. One of the structure is rotated towards 180 degree in the plane of paper. As a result, stereomers 3 and 4 are identical and represent only one stereomers. These isomers 3 and 4 is however different from both in first and second, whereas 1 and 2 optically active, third and fourth is not. This is due to the reason that is the stereomers have a plane symmetry. One half of the molecule is mirror image of the other half. As a result, the stereomers 3 and 4 is not chiral dissymmetric even though it contains two chiral carbon atoms. Consequently, the stereomers 3 and 4 is optically active, such as optically inactive compounds whose molecule is superimposable on its mirror image in spite of presence of chiral carbon atom is called mesocompound. It may note that a mesocompound is optically inactive because the rotation caused by one half of the molecule is exactly cancelled by the equal opposite rotation caused by the other half of the molecule. In other words, optically inactive of mesocompound is due to the internal compensation within the molecule. On the other hand, the optically inactive the racemic modification is due to the reason that the rotation caused by the molecule of the enantiomer is actually cancelled by the equal opposite rotation caused by the same number of molecules of the other enantiomers. In other words, the optically inactive of the racemic mixture is due to the external compensation due to the other molecule. From the above discussion, it follows the tartaric acid exists in the three stereoisomeric forms. Positive is tartaric acid and negative is tartaric acid. And the mesotartaric acid racemic modification positive negative tartaric acid can be obtained by mixing equimolar amount of first and second positive tartaric acid and the negative tartaric acid. Since a racemic modification contains two compounds, it can be resolved. A mesocompound, on the other hand, can be resolved since it consists of molecule only one stereomers. Relationship between enantiomer and the mesocompound. Let us again consider the three stereomers of tartaric acid and inspection of the structure of the positive tartaric and negative tartaric acid. Mesotartaric acid reveals that they are not the mirror image of each other nor can be inconverted by the rotation of outer carbon-carbon bond. Thus, the positive tartaric acid and the mesotartaric acid are diastereomers. Also, negative tartaric acid and the mesocompounds being diastereomers, and the properties of mesotartaric acid are different from those of positive tartaric acid or negative tartaric acid shown below. Trio and erythrodiastereomers, molecules of the type containing two stereogenic centers have been extensively used in the mechanistic study of special nomenclature has been evolved for such systems. This nomenclature is based upon the name of four carbon atoms, sugars, erythros, and threos. If the two like groups A is the position formula are the same sign, then the hydroxyl group is erythros and the isomer is called isomers. If a result the opposite sign, the two hydroxyl groups in threos is the isomer is called three isomers. As a nutrition consideration, consider the diastereomers of 3 bromo 2 beta nor in figure 3.19. 3 isomer of 3 bromo 2 butanol. As the first side in it might appear the feature position formulation in should be accurately represent the diastereomers of compound containing two chiral carbon atoms having. However, a closer look at the models from the represent the molecule in such less stable eclipse form the crowding between the substance C2 and the C3 maximum. But the real shape of the molecule is not like that. It is all more logic compound 2 and arrangement in which C2 and C3 rotate in the angle of 180 rotation as well as their substitution and the part of possible in the staggered form. Therefore, while considering the reaction of a molecule, it is usually desirable to receive the molecule in the actual staggered form rather than it is hypothetical eclipsed form as shown in the feature position. The two best way of represent the such molecule in the most stable staggered form is the Shor's representation and the Newman projection formula. The feature projection formula can be easily transferred into Shor's representation by the making the eclipse form and then rotate through an angle of 180 degree rotation around the C2 and the C3 bond as figure 3.20. Similarly, the feature position formula of erythro and three bromo 2 butanol is transferred to the Newman position formula by the first making the eclipse form and then rotating through an angle of 180 degree around the C2 and C3 shown as figure in 3.21. A comparison of the above three representation as may be helpful. The feature formula clearly shows a glance whether one is dealing with the erythros and the trio form is Shor's and Newman formula but do not equally require a mental process of rotation about the C2 and C3 until one can decide about it, which is when further the Shor's formula are quite convenient to represent eclipse as well as staggered form, but the Newman projection formula but the eclipse form look awkward. Yet another method of representing compounds containing two stereogenic centers has been my flying gas formula shown in figure 3.22 for erythro and 303 bromo 2 butanol. Optically isomerism in compounds containing more than two stereogenic centers or chiral carbon atoms from the above discussion, it follows that the number of stereons depends upon the number of stereogenic and the chiral carbon present in the molecule. For compounds containing the stereogenic centers, there are two stereomers and isomer, for example, containing the two dissimilar stereogenic centers. The number of stereomers is for working on similar lines. We conclude that compounds containing and dissimilar stereogenic centers exist in 2n stereomers. To illustrate this, let us consider 6 carbon atoms. It has 4 dissimilar stereogenic centers and hence exist in C4 is equal to 16 diastereomers. All these isomers known as correspond to the D and N form of allose, heterose, glucose, mannose, glucose, indose, galactose and talose. On the other hand, glucose is one of these 16 isomers. If however any one of more than n chiral atoms becomes identical and the number of stereoisomers is always less than the productive and the basis of 2n rule. Calculation of the stereomers, oblique isomers and the mesoforms. The total number of stereomers, optically isomers and mesoforms depends upon the nature of the molecule and the number of stereogenic centers or chiral carbon atom contains the following cases are when the molecule is asymmetrical and contains an stereogenic center, chiral carbon atoms. In the non-optical isomers are 2n, number of meso compound is 0 and the total number of stereomers is optical plus meso is equal to 2n. For example, 2,3-dibromobutanoic acid is symmetrical and has two dissimilar chiral carbon atoms. Therefore, the total number of optical isomers is 2 raised to power 2 is equal to 40 and the number of meso compound forms is 0. The stereoisomers is 4. There are second is when the molecule is symmetrical and has a number of stereogenic centers of the chiral carbon atoms, the number of stereomers is calculated as follows. The number of optical isomers is and 2 and raised to power n minus 1. The mesoforms is 2 raised to power to n by 2 minus 1. Total isomers is equal to 2 n minus 1 plus 2 n by 2 plus 1. For example, tartaric acid has a total number of stereomers as calculated below. Optically isomers is 2 and the mesoforms is 1 and the total isomers is 3. The structure of 3 isomers are already given in page 130. When the molecule is symmetric and has own number of stereogenic centers, the number of stereomers is calculated as follow. Number of optical isomers is n raised to power n minus 1 minus n 2 raised to power n by 2 minus 1 by 2. Number of mesoforms is equal to 2 raised to power n by 2 minus 1 by 2. Total number of stereomers is equal to 2 n minus 1 is equal minus 2 raised to power n by 2 minus 1 by 2 plus 2 n by 2 minus 1 by 2 is equal to n minus 1. But trihydroglutaric acid has 3 stereogenic centers and the molecule is symmetric. Therefore, the number of optical isomers is 2 and the number of mesoforms is 2. So, the total number of stereoisomers is equal to 4. It is noted that the C3 in the pair of enantiomer first and third is the stereogenic centers and its chiral forms are identical. This is because interchanging of H and OH C3 in the enantiomer lead to the identical structure. This is best seen by the turning of new structure by 180 degree in the plane of paper. How it is on chiral mesoforms. Member of this set interchanging O and OH at C3 converts one form to the another. 3 and 4th on vice versa. Therefore, C3 is stereogenic center but not chiral center. Such a stereogenic center has also been called as pseudochiral center or pseudosymmetric center. Prochiral and the prochiral molecules. A carbon atom in a molecule is prochiral if the replacement of one of the H atom is substituent atom or a group produce a chiral center. For example, C2 in propanoic acid is prochiral since the replacement of the one H atom C2 by Br produces a chiral molecule. Molecules which contain prochiral are called prochiral molecule and the phenomena is called prochirality. Retination and inversion of configuration. Whenever any chemical reaction is carried out in a chiral product may be same configuration as reactant and may be optically configuration. Configuration of the reactant to the product is the same. Reaction is said to be processed and retention of configuration is the configuration of the product is opposite to that of the reactant and the reaction is said to be processed with inversion of configuration. This case arises when the bond is to the stereo center to the chiral center is not broken but the reaction take place at the same other side in the molecule. The configuration of the reactant is retained in the product. For example, alcohols are converted into toislates or treatment with toisul chloride. Paratoluene sulfonide chloride is presence of pyridine. Second one is when the bond to the stereomers to the chiral center is broken, either the inversion of the retention of configuration may occur as discussed below. Inversion in ascent direction. The attack of the nucleophile always occurs from adjacent direction opposite to the leaving group. As a result, all the ascent reactions are accompanied by the inversion of configuration. This phenomenon was first discovered by the Walton and hence is called Walton inversion. Third part is retention. Two important ways in which the retention of configuration may occur as discussed below. If the two ascent reaction occur in the same stereo and center and one after another, configuration of final product is the same as that the starting material. For example, treatment of 2-bromopropanic acid with dilute and HF gives lactic acid with complete retention of configuration. The retention of configuration here has been explained on the basis of neighboring group participation in which oxygen of the carboxylate ion first H albenyl element Br negative in the ascent reaction to form a lactic acid 2 and thus subsequently undergoes another ascent reaction by the OH ion in the same stereo center to afford lactate ion 3 and complete retention of configuration. If however the retention of first is carried out in the presence of strong alkyl groups and the hydroxide ion compared the carboxylate ion in the normal ascent reaction occur to the give lactic acid 4 and the inversion of configuration. Second one is retention of conjugation may also occur if bond cleavage and bond formation occur on the same phases of chiral molecule. For example, chiral alcohol react with ethynyl chloride to give chlorosulfonate, which subsequently decompose to form allyl chiral halides with retention of conjugation. Thus, this is an example of SNI substitution nucleophilic internal reaction. It has been suggested that SNI mechanism like SN1 mechanism can proceed by ion pairs as shown below. Racemic modification of racemic mixture when equal amounts of rhenium are mixed together, it gives an optically inactive form called the racemic mixture, or the racemic modification is denoted by using the prefix RS or DL before the name of the compound. For example, if equal amounts of positive lactic acid or negative lactic acid are mixed together, we get the racemic mixture positive and or RS lactic acid. You have to see the next. Racemic mixture is always obtained whenever a chiral or a dismetric compound is synthesized in the laboratory from a chiral non-chiral dismetric reagent. This is due to the reasons that there are equal probabilities of the formation of the two enantiomers. For example, consider the formation of 2-butanol, a chiral compound, by nickel catalyzed addition of H2, a chiral agent of 2-butanoin. A chiral compound, the carbonyl is planar, therefore the H2 observed on the surface of the nickel catalyzed can add up equal is of the either phase of 2-butanoin, whereas addition at one phase produce one enantiomer, addition to the other phase produce to the other enantiomers. Figure 3.23 and the two reactions occur at the same rate. Assimilation is always optically inactive because the rotation caused by the molecule of the enantiomer are exactly cancelled by the equal and opposite rotation caused by the same number of molecules to the other enantiomers. The other physical properties of the racemic mixture, such as melting point, boiling point, solubility in a given solvent, etc., are also different from those of enantiomer. For example, the melting point of the either enantiomers of lactic acid is 326 Kelvin, while that of racemic mixture is just 291 Kelvin. Racemization, the process of converting an enantiomer's positive or negative and optically active compound into the racemic mixture, is called racemization. Racemization is normally an undesirable process, and hence, whenever any reaction is carried out, an optically active compound, it is necessary to avoid such reagent or reaction condition which induce racemization. Racemization can occur either by heat chemical reagent, acid and bases, or even by the contact with plain solvent. Some of the more important mechanisms by which mechanisms usually occur in the discussed below. By rotation about carbon-carbon single bond, the optically active of ortho substituted diphenyl is due to the restricted rotation about the carbon-carbon single bond joining the two phenyl cause the cause is the restricted rotation is the presence of the bulky substituents at the ortho position of the two phenyl groups which present them in assuming the plane transition state. These compounds undergo racemization or heating. Thus, when a perpendicular enantiomer of an ortho-substituted diphenyl is heated, the heat supplied overcomes the energy barrier between the enantiomers. As a result, the positive enantiomer is converted the enantiomers of the vice versa, and ultimately a racemic modification results. For example, 6,6-dinitrophenoic acid racemized when heated. Next one is by analyzation, optically active hydroketones having a hydrogen atom on the alpha chiral atom undergo racemization or treating with an acid or base. For example, acid catalyzed analyzation. Next one is base catalyzed analyzation. In other reaction, racemization occurs through the immediately of the planar enol 1 and the enolate ion 2. The protonation of 1 and second either phases top or below can equal with equal probability of yield of a racemic modification. For example, base catalyzation of a negative lactic acid or positive has been shown below. Third one is by SN1 mechanism. Racemization of optically active secondary halides such as 2-chlorobutane occurs when treated with Lewis acid with such as AlCl3. Under this condition, alkyl halide is undergo ionization and by an SN1 process to form a carbocation being planar. The recombination of the carbocation with the halide ion can carbon with from either side with unequal probability resulting in the regimation. Fourth part is SN2 mechanism. Optically active halides having the halogen on the chiral carbon can also undergo respiration by SN2 mechanism. For example, when a solution of positive or negative to iodobutane is treated with NaIN acetone undergo respiration to give positive negative to iodobutane. When 2 iodobutane 1 is treated with I negative ion, it undergo Walden inversion SN2 reaction to give to iodobutane 2, which is the enantiomer of 1. Now iodobutane 2 undergo Walden inversion to give enantiomer 1. As a result of these two repeated Walden inversion, ultimately a 50-50% of the two enantiomer is obtained. Optically active, the 2 butadiene undergoes racemization. Resolution. As stated above, a racemic mixture contains equal amount of the two enantiomers. The process of by which racemic mixture can be separated into positive and negative enantiomer is resolution. Since the enantiomer have identical physical and chemical properties except towards the optically active reagents, they cannot be separated by the usual techniques such as fractional distillation unless the solvent are optically active, fractional distillation, chromatography unless the adsorbents are optically active, etc. Therefore, special methods are used to achieve their separation. Some of the important methods to resolve racemic which are discussed below. First is mechanical separation. This is the most classical method and that is used by the pursuit to separate the enantiomers of sodium ammonium titrate. Sometimes when a concentrated solution of the racemic mixture is allowed to crystallize, two types of crystals may separate out. One type being a mirror image of the other. The two crystals can be separated by the hand picking uses a pair of tweezers and magnifying glass or a microscope. Imitation this modified method is most laborious and the time consuming and applicable to only those compounds which give a definite crystal of enantiomer so that they can be easily undistinguished. Second is biochemical methods. Certain organisms use enantiomer as their food leaving out of other. For example, Penicillium gallosium consumes only the positive tartaric acid and the tartaric acid can be resolved by the adding Penicillium gallosium to it, which consumes positive tartaric acid and the leaving should negative tartaric acid. Limitation. Since one of the enantiomer is destroyed and this method is not satisfactory. Further, this method cannot be used to separate poisonous compounds which may kill the microorganism. Third one is a chemical method. This is the most widely used method for separating racemic mixture. This is based on the principle that when a racemic mixture is treated with optically active agent, it is mixture of the isomers. Since the isomers are the mirror image of each other, different physical chemical properties. Melting point, boiling point, stabilities, and hence be separated by the physical methods. Properties such as melting point, boiling point, stability, and the optically active reagent is then removed by the stable method, leaving behind the pure enantiomers. To ensure this method, we aside the isolation positive negative tartaric acid when treated with an optically active base such as positive uracil and positive negative tartaric acid give rise a mixture of two diastereomers, positive tartaric acid and positive uracil and the negative tartaric acid and the positive uracil. These two compounds being diastereomers have widely different solubilities, hence can be separated by the fractional crystallization. After the separation, each diastereomer is purified by the recrystallization and treated separately with dilute HCl to retain the compounds corresponding positive and negative tartaric acid. The whole process is schematic shown below. Similarly, positive and negative base can be separated by the optically active acid such as positive tartaric acid or negative malalic acid. Fourth one is chromatography. Racemic mixture can be treated by the column chromatography using a optically active adsorbent such as starch, lactic acid. When one of the enantiomer gets actively absorbed, elution of the column with a stable solvent first gives the enantiomer which is absorbed strongly and subsequently the more strongly absorbed enantiomer in the way desired separation is achieved. Next is DL and RS nomenclature. The relative, the absolute configuration, the arrangement of the atom or group of the atom are characterized as a particular stereomers is called the configuration. The two terms which are commonly used to describe the configuration of the two stereomers are absolute and relative configuration. By the absolute configuration, we mean the actual arrangement of the atom or group of atom in space of particular stereomers of a compound. The relative configuration, on the other hand, means of arrangement of atom or group of atom in space of stereomers of a compound related to the atom or group of atom of another compound chosen as the arbitrary standard. If the solute configuration of the standard is established by the some unambiguous method, then the relative configuration of the stereomers correlated in factor represent is as absolute configuration. Consider, for example, the lactic acid exists a pair of enantiomer first and two. Each of the enantiomer has a different configuration about the chiral center, one of which is destructive while the other is liberative. How we how we do know which is which? To solve this problem, organic chemists have developed two different conventions are discussed below. First is DL nomenclature DL system. Before 1951, there are no method available for determining the absolute configuration of a compound. Therefore, the relative configuration of all compounds were established with respect to the glyceraldehyde chosen as the battery standard. The two enantiomers of the two compounds were distinguished by the DL and symbol, and the positive enantiomer are given to the symbol D and the assigned to the configuration 3 in them, which OH lies towards right and H lies towards the left, and CHO as the top and the CH2 lies at the bottom. The future position, on the other hand, positive glyceraldehyde are given to the symbol was configuration 4 and OH is towards left to the H atom towards right. The relative configuration of the compounds are stable as follows. Any compounds that will be prepared for the converting into D-glyceraldehyde will belong to the D series. Similarly, any compound that can be prepared from the or converted into L-glyceraldehyde will belong to the L series. These correlations are based upon the general principle that if reaction does not involve the cleavage of a bond to the chiral center, the configuration about the chiral center is retained. For example, D-positive glyceraldehyde can be converted into negative glyceric acid by simple oxidation, and the configuration of glyceric acid thus obtained must be D. Similarly, positive glyceraldehyde obtained from L-glyceraldehyde with the following sequence of reaction is assigned L configuration. Although the configuration assigned by Fischer, D and L-glyceraldehyde purely attributed by the time, but subsequently in 1951 X-ray diffraction studies and sodium rubidium titrated by the Bizovet proved that they are in fact correct. Thus, the relative configuration of D-glyceraldehyde and L-positive lactic acid discussed above in fact represent their absolute configuration. Following the above procedure to absolute configuration of a number of optical active compounds have been established, it may be noted that there is no simple relationship between the absolute configuration of a particular enantiomer and the direction of a rotation of polarized. In other words, compounds having the same configuration may have different signs of rotation. For example, D-glyceraldehyde and D-negative glyceraldehyde acid have the same configuration but different signs of optical rotation. Similarly, compounds having different absolute configuration may have the same signs of rotation. For example, L-glyceraldehyde and D-negative lactic acid have opposite configuration but the same signs of rotation. For compounds containing several chiral carbon, the configuration at the stereocenters is related to the glyceraldehyde, while the configuration is to the other stereomers determine the relative of the C5 correlated to the glyceraldehyde, while the configuration at the other stereomers are determined relative to the first. It is naturally occurring glucose OH group in C5 is assumed to the reverse assigned to the D-glucose. Limitation. Sometimes some compounds can be correlated by the sequence of reaction to the known as the compounds is D compound, and the different sequence of reaction is known as L compound. This matter is quite cumbersome to apply such compounds which contain two or more chiral carbon atoms. Because of this difficulty, DL system is seldom used. This except for carbohydrate and amino acids. As nomenclature absolute configuration. The limitation of the DS system have however been removed by the ambitious system developed by the R.S. Chan, England, C.K. Ingold, and V. Perlog, Switzerland, called Chan Ingold Perlog CIP system, and simply the RS system. The designation of the absolute steriochemistry and optically active compounds according to the system involve the following step. 7. Impurity of a number of first, second, third, and fourth assigned to the each of the four atoms or group of atom attached to the chiral carbon in the accordance with the following sequence rules. Second rule: one of if the four substance attached to the carbon for all, therefore priority number of decided on the basis of their atomic numbers. The atom of atomic number gets the higher priority. Thus, all the compounds bromochloroidomethane. The order of decreasing priority is iodine first, bromine second, chlorine third, and hydrogen fourth. If the two atoms attached to the carbon or isotopes of same element, the isotope of higher mass number gets the higher priority. For example, the compound alpha deuteroethyl bromide, the order decreasing priority is Br first and CS3 second, and D is 3 and H is 4. Second rule is 2. If the relative priority of the two groups attached to the chiral carbon cannot be decided on the basis of rule 1, it may be decided by comparison the atomic number of the next atom in the group, and so necessarily working outwards from the chiral carbon to the first point of the difference. In other words, if the first atom attached to the chiral center is the same in the both groups, compare the atomic number of the atom attached to each of the first atoms. Consider the, for example, 2-butanol. The first atom attached to the chiral carbon and themselves carbon atom in CS3 group. In second atoms are hydrogen, while in the CS3 CS2 group have the CHH. Since carbon is a higher atomic number than H, CS3 CS2 group has a higher priority over the CS3 group. Thus, the complete sequence of priority of the 2-butanol is therefore OH is first, CS3 CS2 is 2, and CS3 is 3, and H is 4. Second rule: third is double bond or triple bond are treated as they are have duplicate or triplicate single bonds. In other words, each doubly bonded atom is duplicated and each triply bonded atom is triplicated. Thus, to state this, consider glyceraldehyde and the 3-chloropentane 1-ion as example. In glyceraldehyde, OH is the highest priority. All the substance has, and the O and H and CH get priority or H. Thus, the complete sequence of priority is OH is first, CS2 is second, CS2 is third, and H is 4. Yes, 3-chloropentane 1-ion and the Cl atom is the highest priority and over the other atoms. Thus, the complete sequence of priority, then the Cl first, C triple bond, CH is 2, and the CH2 CH3 is 3, and H is 4. A phenyl group C6H5 is considered as a head and Coulombic structure. Comparison of priorities of phenol, acetylene, vinyl, and isopropyl group. In order to assign priority of each of these, let us consider the number and nature of atoms attached to the first bond in each case. In phenyl and acid group, the first carbon is connected to the other group's atom, while in the vinyl and isopropyl group, the first carbon is connected to only two other carbon atoms. Therefore, phenyl and the acetylenic group have higher priority over vinyl and isopropyl group. To decide the relative properties of the phenyl acetylene group, we must proceed further along the chain in phenyl groups who further connected to the CCH, while the third is duplicated carbon. On the other hand, acetylenic group only the CCC is further connected to the CCH, while the other two are duplicated carbons. Therefore, the phenyl group get a higher priority over acetylenic group. To decide the relative properties of vinyl acid isopropyl group, let us consider the nature of and the number of atoms attached to the single carbon. Second carbon. In vinyl group, the carbon atom is connected to the one carbon duplicated and the two hydrogen atom, but is isopropyl group. The second carbon is connected to only hydrogen atom. Therefore, vinyl groups takes priority over the isopropyl group. This in light of above discussion. The complete priority sequences CH5 is greater than the C triple bond CH is greater than the CH double bond CH2 is greater than the CH3 twice. Step 2 on the once the order of priority of the four atoms or group directly attached to the chiral carbon atom has been decided, the molecule is then oriented in space in such a way that the group of lowest priority is decided away from us. A good analogy of this situation is the steering wheel of a motor car and the group of lowest priority representing the steering rod and the three other atoms or group representing the three spokes of the wheel. If analyzing group of highest priority or group of second priority, then the group is third priority. First, second and third. The eye moves in the clockwise direction. The configuration is specified as R. Right in rectus means right, and the anti-clockwise the configuration is specified as S. Latin is left. And this is the example you have to see. Next one is assignment of RS configuration of your future position. The assignment of RS configuration of future position of organic compounds involve the following steps. Assign the priorities of the four atoms or group attached to the chiral carbon. Second step is if the group or if the atom or group of lowest priority occupies horizontal position left or right of the future projection formula of organic compound, then make two interchanges of the atom or group in such a way that the atom or group of lowest priority is placed either vertically upward or downward. This is done. Example illustrate the above procedure. Assignment of RS configuration to the future projection. When a compound contains two chiral carbon atoms but different isomers are possible, having the following configuration 2R, 3R, 2R, 3S, 2S, 3R and the 2S and 3S. First are discussed. Each carbon is separately assigned RS configuration. Let us RS configuration to carbon 2 and 3 is plus positive tartaric acid. In this example is R configuration. Thus the configuration of positive tartaric acid, by knowing the configuration of enantiomers, the configuration of the two enantiomers can be processed easily in below. It may be noted that the rotation of paper slide has nothing to do RS non-rotation, which give only the direction in which the eye travels when the visually molecule head in the arbitrary manners. Thus, the RS compound may be either restorative or reveratory. This method discussed above in the quite time consuming. Therefore, a simple rule has been formulated as RS configuration to the chiral organic molecule as in 3D physics projection and the golden rule, and this is discussed below. Golden rule assign priorities of the four atoms of the attached to the chiral center without making the no interchanging the atoms or group. Find out the configuration if the atom or group lowest priority occupies vertical upward downward position. The future position and the configuration obtained upon gives the actual configuration of the molecule. If however the atom or group lowest priority occupies horizontal position left to right in the future position, then changes the configuration from RS to vice versa. For example, without making the two interchange, the configuration turns into R since the atoms is lowest priority H occupies vertically position in the future position. Therefore, the correct configuration of the compound remains to be R. If without making the two interchanges, the configuration turns out of the R since the atom of the lowest priority H lies in the horizontal position in the future position. Therefore, the R changes R to S. The correct configuration is S. Without making the two interchanges, the configuration turns out of the S since the atom of the lowest priority H occupies the horizontal position in the future position. Therefore, the change is S to R. Thus, the correct configuration of the compound is R. Simple method for converting flying wedge to the 3D formula. Future position: the atom or group shown in the below the plane of the paper. The flying formula is kept in the bottom of the future position formula. In the remaining three atom or group arranged in the same sequences clockwise or anti-clockwise in the plane in the flying wedge formula. For example, as convert the flying wedge formula first and the flying future position formula 2 is the CS3 group below the below. Plane of paper is placed at the bottom of the fixed position formula 2 and the remaining three groups OH, H and COH are in anti-clockwise direction as they and arranged in the same sequence in the fixed position formula 2. Therefore, more than the one fixed position formula can be written as the given chiral compounds. Therefore, to get the most conventional fixed position formula in which the vertical portion of the projection formula represents the lowest possible carbon chain with the most oxygen carbon atom to the top. Make two interchanges of atoms and group attached to the chiral carbon atom. For examples, thus the position second and third, the French formula first and represent S-lactic acid. And thus the flying wedge formula fourth and the fixed position formula fifth and sixth all represent alglyceraldehyde. Simple method for converting the fixed position formula to the flying wedge formula 3D formula. The atom or group is in the and the bottom of the fixed position formula is kept below the plane of the paper is flying wedge formula. The remaining three groups are arranged in the same sequence clockwise or anti-clockwise as they appear in the fixed position formula, keeping one of the atom group lying in the horizontal axis next. Fixed position formula of both the plane of the paper in the flying wedge formula is let note the sequence all the atom or group in the both formulae should be same. For example, to let us whether flying wedge formula second actually present or lactic acid, the interchanging of the atom or group in such a way that the atoms of lowest priority lies below the plane of paper. Assign priorities of to the four atoms group attached to the chiral center. You will find the formula third and hence the formula second actually present the RS lactic acid. For further illustration, the consider the fixed position formula S is to butanol fourth. Hence, fixed position formula fourth and flying wedge formula fifth and sixth are represent S to butanol. Next one is geometric isomerism. Like optical isomers, geometric isomers are also configuration isomers since they are interconverted only by the breaking or remarking of covalent bonds. Further, since geometric isomers and the mirror image of each other by the but configuration isomers which are not run mirror image of each other and called diastereomers. Therefore, geometric isomers may also be regarded as diastereomers. For some important aspects of this kind of diastereomers are discussed below. Geometric isomers inherit rotation around carbon-carbon double bond. We know that double bond consists of a sigma and a pi bond. Thus, the pi bond is formed in the sideways overlapping of an p orbital of the two carbon atoms above and below the plane of carbon atoms. If one of the carbon atom with double bond is rotated with respect to the other p orbital will be known or overlap the pi bond should break. Figure 3.24. But the breaking of the pi bond requires 251 kJ per mole of the energy which is not provided by the collision of the molecule at the room temperature. Consequently, the rotation about a carbon-carbon double bond is not free but is strongly hindered or restricted. In other words, the pi bond prevents free rotation. The carbon atom of the double bond with respect to each other is a hindered rotation. The relative position of the atom or group attached to the carbon atom of the double bond it get fixed. For example, HA and HB in figure 3.25 can not be exchanged their position by rotation C1 and except C2 without breaking the bonds. As a result, many substituted alkanes cannot be isomers which differs from each other only in the relative position of atom or groups in space around a double bond. For example, butene and can exist following the two forms first and second. First is butene and the second is trans to butene. Both these isomers have the same structure formula but differ in the relative spatial arrangement of hydrogen atoms in methyl groups around the double bond. Such isomers which have the same structural formula but different in relative spatial arrangement of atom or groups double bond are geometric isomers. The phenomenon is geometric isomerism, and the geometric isomerism is a type of space or sterioisomerism. Now, isomerism first in which the two similar atoms or group lie in the same side of the double bond is called cis isomers, while the isomerism two in which the similar group or atom or group lying in the opposite side of the double bond is called trans isomers. It is because of the reason that geometric isomerism is called the cis trans isomerism. necessary and the sufficient condition for the geometric isomerism. It may be mentioned that all compound containing carbon-carbon double bonds do not show geometric isomerism. The necessary condition for an alkene to exhibit geometric isomerism is that each of the carbon atom of the double bond must be different. Substituent much may be same or different. The alkene of the type ABC, CAB and ABC can show geometric isomerism. However, geometric isomerism are not possible if both the double bonded carbon atom carry the two similar substituents. This is because in some such cases the two possible configurations are in fact identical as shown below. As it is because this region the terminal alkenes and the propane but 1 in 2-methyl prop 1 in etc. alkene carrying identical substitution on the double bonded carbon atoms such as 2-methyl but 2-1-in and the 2-methyl but 2-in etc. do not show geometric isomerism. Determination of the configuration or geometric isomers. We have discussed about the undistributed alkanes carrying the two different substituents on each of the carbon atom double bonding in extremes, strings and translocation as we know which distributes in the basis on the basis of their physical properties. Melting point in general, the melting point of trans isomer is higher than the corresponding cis isomers. In the trans isomer, the two similar atom or group lie in the opposite side of the double bonding. Therefore, the molecule are symmetric and pack well in the crystal lattice. On the other hand, in the cis isomer, the two similar atom or group lie in the same side of the double bonding. Therefore, these molecules are unsymmetric and hence do not pack well in the crystal lattice. As a result, the molecular forces of the attraction holding the molecule of the trans isomer in the crystal lattice are much stronger than those holding the molecules of a cis isomer. Consequently, the melting point of a trans isomer is much higher than that of a corresponding cis isomer. For example, Murionic acid isomer is melting point is 403 Kelvin. Fumaric acid trans isomer is melting point is 575 Kelvin. Aluminic acid since trans isomer melting point is 341 and the cinnamic acid trans isomer melting point is 406 Kelvin. Sign is solubility in general. The solubility of since isomer is higher than the corresponding trans isomer. This reason molecules of since isomer are weakly held in the crystal lattice and the corresponding trans isomer expand above. Thus, the malonic acid solubility is 79 gram per 100 ml of H2O, whose malonic acid solubility is 0.7 gram per 100 ml of H2O. Third is dipole moment. The general cis isomers have higher dipole moment than the corresponding isomers which have even zero dipole moment. With the trans atomic or group on which atom of the double bonded are the same. This is due to the reason is trans dipole moment included in the other to the angle of approx 60 degree. Hence, the finite dipole moment on the other hand, the trans isomers develop in the opposite position, hence cancel each other. Lesson is since mu is 1.85 d and trans mu is equal to 0. Anyway, we have noticed that there is trans isomer and necessarily have zero dipole moment. For the example, trans pen 2 in and a definite dipole moment through the some smaller corresponding cis isomer. This reason is the dipole moment of CCS3 and CS2 and CS3 bonds are not equal. Through these two dipole oppose each other and do not exactly cancel each other, and hence trans pen 2 in has a small finite dipole moment. Thus, trans pen 2 in is much less polar than cis pen 2 in. First one is boiling point. In general, the boiling point of the cis isomers are higher than those of the corresponding trans isomers. The reason being the possible boiling point of isomeric compounds depends on the dipole-dipole interactions. So the cis isomers have higher dipole moment, more polar than the corresponding trans isomers, less polar. Therefore, the boiling point of cis isomers are higher than those of their corresponding trans isomer. For example, since butane mu is equal to 0.4, and I have used in further examples. On the basis of the chemical reaction formation of alike compounds, these methods are more dependable than the physical method. In the cis isomers, the reacting groups being on the same side of the double bond interact with each other, resulting in the formation of the allyl cyclic compound. On the other hand, in trans isomers, the reacting groups being on the Opposite sides of the double bond do not interact with each other to form a silane compound. This malonic acid, since isomers on heating at 243 Kelvin, little avoids melting point, readily loses a molecule of H2 to form malonic anhydride. Since the two CO carboxylic acid groups are near to each other, however, at this temperature, fumaric acid transisomers do not form an anhydride, since and the two COH groups are far apart. However, and the fumic acid is heated in 573 Kelvin, close to the melting point. It loses the molecule H2 to give the same anhydride malic anhydride, since anhydride to give malic acid and is not a fumic acid. Second is on the basis of optical properties of the stereochemistry formed during the hydration and bromination of reaction. The optical isomerism of products formed depends upon the stereochemistry of the reactants. The hydration of the alkenes with dilute KMnO for a solution or osmine tetrahydride solution disulfide treatment is a cis addition process. Therefore, the cis isomers give meso compounds while the trans isomers give racemic positive negative products. For examples, lactic acid in constant bromination, an alkene is a trans addition process. Therefore, the trans alkene gives meso products, while cis alkenes give racemic products. Trans butene gives meso 2,3-dibromobutane and cis butene in Br2 in CCl4. In trans addition gives to the 2 positive negative 2,3-dibromobutane. In this system of the nomenclature we have seen about the cis and trans notation. Notation can be used without any ambiguity to describe the spatial orientation of the two identical form atoms around a double bond in the substituted alkane. However, in case of the tri and tetra substituted alkane, in which the 3 or 4 different atom or group are attached to the carbon atom to the double bond, it is difficult to assign cis and trans notation to the pair of geometric isomers. To illustrate this, let us consider the following geometric isomers of 1 bromo, 2 chloro and 1 ethane, in which 4 different atoms are attached to the double bonded carbon atoms. If we have seen Br and Cl attached to each other, we can easily accurately I and Cl assist to each other. It is difficult to name each substances each are in the cis and trans isomer. In order to avoid this ambiguity, is a general system of nomenclature for designating the configuration isomerism about a double bond has been developed. This system is called E and Z system and is based upon the parity sequence rules originally developed by the Chahan, Ingold and Perlow to describe the configuration about the chiral carbon atom in the molecules. The main point of E and Z discussed below. First is following the sequence of the rules described for optically active compounds RS system. In section A, priority order is assigned to the two atom or group attached to the each other carbon atom or double bonded. Second, if the atom or group higher priority on each carbon atom or double bonded are in opposite sides of the double bond, the configuration of designated as each taken from the German word antagon across. If one on the other hand the two atom or groups of high priority on each other carbon atom or double bonded are on the same side of the double bonded, the configuration is designed as Z taken as the German word German together. Thus, first is E isomer and second is the Z isomers. Let us illustrate this process of the following example. The two geometric isomers of 1 bromo, 2 chloro, 2 fluoro and the 1 iodoethane are. Since we know the atom of higher atomic number of higher priority I is first and the higher priority and the Br2 and carbon atom I and the Cl 1 and has higher priority and F is equal to 2 and the carbon atom 2 and the isomers first as the atom of priority first and Cl having being opposite side of double bonding is designed as the E isomers, while the isomer 2 will these atoms of higher priority on the opposite side of the double bond is designed as the Z isomers. Second is the cis and trans isomers of 2 butene can be designed as Z and E butanes respectively. Hence, here 3 is the higher priority than H since the atomic number of the carbon is higher than the hydrogen. Third is similarly malic acid or fulvic acid may be designed as isomers as follows: as the organic compounds containing two or more double bond capable of showing geometric isomers, E and Z isomers double bonded. For examples are E and Z. Next one is geometric isomers: compounds containing two or more double bonds. If compounds have double bond in which two or more different CH, and then four geometric isomers are possible: E E Z E or cis trans Z Z cis, and E Z or trans cis, and E E and trans trans. In other words, the number of geometric isomers in 2n, where n is the number of the double bond in which denoted as the formula applies to only the molecule in which the two ends are different. However, in different indicated number of isomers is first is n raised to power n minus 1 plus n raised to power n by 2 minus 1, where n is the even. Second is n raised to power n minus 1 plus n raised to power n by 2 minus 1 by 2, where n is odd. Oxime geometric isomerism in oximes. Oximes compounds formed in the action of the hydroamine and aldehyde and ketone under weak acidic pH 3.5 to 4 conditions. Acetaldehyde after reaction, acetaldexime, and the benzylaldehyde after reaction, the benzyloxazine. In terms of modern theory of valence bond valency, both the carbon and the nitrogen atom in oximes are sp2 hybridized. This is similar to the hybridization of the carbon atom in ethylene. Hence, the C double bond N double, like that the C double bond C consists of one sigma bond and one pi bond. The third sp3 is optical orbital of the nitrogen contains the lone pair of electrons. Thus, the oxime molecule is the planar about the double bond, and the like alkane exhibits geometric isomers due to the restricted rotation about C double bond N. However, has the prefix in cis, and the photons are commonly used. In case of old oxime derived from aldehyde, since isomer is one of in which H atom and OH lie on the same side of the double bond, and each anti-isomer H and OH lie in the opposite side of the double bond. For example, in case of oxime derived from ketones, the prefix in and indicates the relationship of first group and name and the hydroxyl group. Thus, oximes can also be named as E, and the system of nomenclature is shown as above. Here, OH is always assigned priority first, while the atoms or group the atoms are assigned priority 1 or 2 according with the sequence rules. Determination of the configuration of oximes. First is aldoxime. Aromatic oxime exist in the two geometric isomerism forms called the C note anti forms. Alphatic aldoximes exist only in the one form, the most stable anti form. The configuration of aromatic aldoximes are determined by the first converting them to their corresponding acid aldehyde on the treatment with acid anhydride Ac2O and presence of trace of the acid and the treated in the second solution of Na2SO3. If an such a treatment of the original oxime is generated, the oxime is assigned as the E and the sine isomer. However, the molecular acid and COH is lost in the form of cyanide, and the oxime is called E, Z and anti-isomers. The second is ketoxime. The configuration of geometric isomers aromatic ketoxime. Alphatic ketoxime occurs only in the one form are determined by the Beckmann rearrangement. The ketoxime is treated with acidic reagents such as PCl5H2SO4 associated when the oxime isomerism to be substituted amide to the migration to the AR end, which is anti to the OH group. The structure of the amides thus formed are determined by their hydrolysis to the corresponding acid and the amines. Knowing the structure and the acid and the amines thus form the configuration of the oxime are established. Thus, geometric isomerism in allylic compounds. When we have discussed about the geometric isomer rises when due to the restricted rotation amount in the principal inheritance about the structured double bonds only. For example, allylic compounds with 3 cis-membered rings such as distributed derivatives of cyclopropane, cyclobutane, cyclopentane, and the cyclohexane. Because of their rigid ring structure, also hindered rotation about the carbon-carbon single bond and hence geometric isomerism. To understand geometric isomerism more clearly, we assumed carbon atom of the ring form a plane. This assumption is essentially correct for 3 5-membered ring but not 6 and higher membered ring since they have picard non-planar rings as I'll discuss later in this unit. The plane of the ring is usually drawn horizontal and edge of the ring projected towards as in shaded highly. The substituent atom carbon of the ring are shown in vertical lines. When an atom or a group is placed at the bottom or vertical line, it is said to be above the plane of the ring. When an atom or group is placed at the bottom of the vertical line, is said to be below the plane. Sometimes a broken wedge is used in the indicate a group below the plane of a ring, and a solid line represent a group above the plane. For illustration, geometric allylic compounds consider the following examples: trans cyclopropane 1,2-di carboxyacid, and second is cyclopropane 1,2-di carboxyacid. Distributed cyclobutane and cyclopentanes show 2-position isomers. Each one of the can exhibit geometric isomerism. In contrast, distributed cyclohexanes show the 3-position isomers in each of the can exhibit geometric isomerism. For example, cis-1,2-dimethyl cyclohexane, next is trans 1,2-dimethyl cyclohexane, next is cis-1,3-dimethyl cyclohexane, and next is trans 1,3-dimethyl cyclohexane, next is cis-1,3-dimethyl cyclohexane, next one is trans 1,4-dimethyl cyclohexane, next one is conformational isomerism. We have already discussed in the unit 1 the sigma or the single covalent bond between the two carbon atoms is formed by the overlapping of the sp3 hybrid orbital of each carbon atom along with the internuclear axis. Therefore, the electron distribution within the molecular orbital, the form of cylindrical symmetrical on the interval axis is shown figure in 3.26. Due to the cylindrical symmetry of sigma molecular orbital rotation about the carbon-carbon single bond in the almost free, and it rotates very little energy for rotation. As a result of this almost free rotation in the molecule, and alkane can have different shape and different relative arrangement of the group in the space. And this definite number of monetary arrangement of the group in the space which result of the rotation about a single bond are called conformation, and the rotation isomer or simply rotamers. Let us now apply the concept of free rotation about the carbon-carbon single bond of the alkanes such as the ethane, propane, and butane and molecule, and discuss this conformation. Conformation of ethane. In ethane CH3 molecule, the two carbon atoms are connected to the sigma bond in which of the methyl group is the ethane molecule is kept fixed, another is rotated in the CC bond. A large number of momentary arrangement of the hydrogen atom on the one carbon atom and respect to the hydrogen atom and the other carbon atom in the space are obtained. This immediate number of momentary arrangement of the atom in the space represent the conformation of ethane. In all the conformation, the basic structure of the ethane molecule and various bond angles and the bond length remains the same. Out of the infinite number of the possible conformation of ethane, only the two extreme ones are important. These are the called staggered and eclipsed in conformation. Two-dimensional 2D representative conformation. The dimensional structure can be represented on a two-dimensional 2D surface with the feature projection figure 3.14. On series drawback of the projection formula is that they present the molecule in the unfavorable eclipse formation. However, while discussing the reaction of a molecule is usually undesirable received molecule in actual staggered form rather than the hypothetical eclipse form mentioned in feature projection. Therefore, the outcome this difficulty, the confusion of molecule are usually represented by the following three methods or formula. This is a simple method representing the three-dimensional formula on paper. The formula is viewed silently from each from the right and the projected the form paper. The bond of the right and projected the paper. The bond between the two carbon atom is drawn diagonally and the slightly elongated or cleared in the lower left, and the carbon is considered to be towards the front and the upright hind carbon towards the back. The source represents the staggered and eclipse formation of the ethane is shown in figure 3.27. That is flying waves represented in the formula. The bonds containing the two carbon atoms are drawn horizontally in the plane of symmetry, as represent the bond lying in the above the plane of the paper. Ordered line are used in the not bonds lying within the plane of the paper and dotted line in the stand of the long line the paper of the paper. Flying waves dotted line waves the plane staggered and the eclipse formation of the thin is figure 28. Third one is the Newman projection formula. Newman revised derived a simple and highly represented usually method to representing the three-dimensional formula on paper. After the name the Newman projection, this projection formula are obtained by being movable along the bond joining the two carbon atoms. The carbon atom near the is represented the point by the three carbon atoms and a group attached to the three equally spaced 120-degree radii. The carbon atom farther above the is by a circle, and the three atom are group attached to the three equally spaced radial extension. The Newman projection of staggered and eclipsed formation and ethane as shown in figure 2.29. Relatively solubility of staggered eclipsed configuration of ethane. In staggered configuration, each of the hydrogen atom on the front carbon lies exactly in between the hydrogen atom on the back carbon in the hand. In other words, in this configuration, any two hydrogen atom or adjacent carbon atom non-bonded hydrogen as far apart as possible. Intermolecular hydrogen and distance is 3.1 angstrom and 309 picometer. As a result, the repulsion between the electron cloud sigma bond of non-bonded hydrogen atom minimum. On the other hand, in this eclipse formation, the hydrogen atom as carbon lies exactly behind the hydrogen atom in front. In other words, non-bonded hydrogen atom are quite close. As a result, the electron cloud to the sigma bond and non-bonding hydrogen atom repel to each other and rises the energy of eclipse configuration relative to the staggered formation. Thus, staggered configuration of the ethane should be most stable eclipse formation experiment in which staggered configuration of ethane is 12.55 kJ per mole and about the 3 kcal mole per mole and the eclipse formation. The variation of energy and the configuration of ethane with the rotation